The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, we're ready to start the 11th lecture. We're still in the middle of sketching, and indeed, one of the reasons why we did not talk about hyperbolic functions is that we're running just a little bit behind, and we'll catch up a tiny bit today, and I hope all the way on Tuesday of next week. So let me pick up where we left off with sketching. So this is a continuation. All right, I want to give you one more example of how to sketch things, and then we'll go through it systematically. So the second example, we did one example last time, is this. The function is x plus 1 over x plus 2. And I'm going to save you the time right now. This is very typical of me, especially if you're in a hurry on an exam. I'll just tell you what the derivative is. So in this case, it's 1 over x plus 2, the quantity squared. Now, the reason why I'm bringing this example up, even though it'll turn out to be a relatively simple one to sketch, is that it's easy to fall into a black hole with this problem. Okay? So let me just show you. This is not equal to 0. Okay, it's never equal to 0. So that means there are no critical points. Okay, at this point, many students who have been trained like monkeys to do exactly what they've been told suddenly freeze and give up because there's nothing to do. So this is the one thing that I have to train out of you. You can't just give up at this point. So what would you suggest? Okay, can anybody get us out of this jam? Yeah. Right. So the suggestion was to find the x values where f of x is undefined. In fact, so now that's a fairly sophisticated way of putting the point that I want to make, which is that what we want to do is go back to our pre-calculus skills and just plot points. Okay? So instead, you go back to pre-calculus and you plot some points. That's a perfectly reasonable thing. Now, it turns out that the most important point to plot is the one that's not there, namely the value at x equals -2, which is just what was suggested. Namely, we plot the points where the function is not defined. Okay? So how do we do that? Well, you have to think about it for a second, and I'll introduce some new notation when I do it. If I evaluate 2 at this place, actually I can't do it. I have to do it from the left and the right. So if I plug in -2 on the positive side from the right, that's going to be equal to -2 plus 1 divided by -2, a little bit more than -2 plus 2, which is -1 divided by, now this denominator is -2, a little more than that, plus 2, so it's a little more than 0. All right? And that is, well, we'll fill that in a second. Everybody's puzzled. Yes?
I thought that you were looking at the derivative.
No, that's the function. I'm plotting points. I'm not differentiating. I already differentiated. Okay? I already got something that was a little puzzling. Now I'm focusing on the weird spot. Yeah, another question. Wouldn't it be a little less than 0? Okay, so that's a very good point, and this is a matter of notation here and a matter of parentheses. So wouldn't this be a little less than 2? Well, if the parentheses were this way, that is 2 plus with a minus after I did the 2 plus, then it would be less, but it's this way. Okay? So the notation is you have a number and you take the plus part of it. That's the part which is a little bit bigger than it. All right? And so this is what I mean. All right? And if you like here, I can put in those parentheses too. Yeah, another question. Why doesn't the top one have a plus? The only reason why the top one doesn't have a plus is that I don't need it to evaluate this. It's going to, and when I take the limit, I can just plug in the value. Whereas here, I'm still uncertain because it's going to be 0. And I want to know which side of 0 it's on, whether it's on the positive side or the negative side. All right, so this one, I could have written here a parentheses 2 plus, but then it would have just simplified to -1 in the limit. All right, so now I've got a negative number divided by a tiny positive number. And so somebody want to tell me what that is? Negative infinity. Okay, so we just evaluated this function from one side. And if you follow through the other side, so this one here, you get something very similar, except that this should be, whoops, what did I do wrong? I didn't want to, yes, I meant this. Okay, I want it -2, the same base point, but I want to go from the left. All right, so that's going to be -2 plus 1, same numerator, and then this -2 on the left, plus 2, and that's going to come out to be -1 divided by 0 minus, which is plus infinity. All right, or just plain infinity. You don't have to put the plus sign in. Okay? Now, so this is the first part of the problem. And the second piece to get ourselves started, you could evaluate this function at any point. This is just the most interesting point. All right? This is just the most interesting place to evaluate it. Now, the next thing that I'd like to do is to pay attention to the ends. And I haven't really said what the ends are, so the ends are just all the way to the left and all the way to the right. So that means x going to plus or minus infinity. All right, so that's the second thing I want to pay attention to. Again, this is a little bit like a video screen here. And we're about to discover something that's really off the screen in both cases. All right, we're taking care of what's happening way to the left, way to the right here. And up above, we just took care of what happens way up and way down. All right, so on these ends, I need to do some more analysis, which is related to pre-calculus skill, which is evaluating limits. And here, the way to do it is to divide by x in numerator and denominator, right, as a 1 plus 1 over x, 1 plus 2 over x. And then you can see what happens as x goes to plus or minus infinity. It just goes to 1. All right, so no matter whether it's x is positive or negative, when it gets huge, these two extra numbers here go to 0. And so this tends to 1. So if you like, you could abbreviate this as f plus or minus infinity is equal to 1. All right, so now I get to draw this, and we draw this using asymptotes. So there's a level, which is y equals 1, and then there's another line to draw, which is x equals -2. All right? And now, what information do I have so far? Well, the information that I have so far is that when we're coming in from the right, that's this to -2, it plunges down to minus infinity. So that's down like this. Okay? And I also know that it goes up to infinity on the other side of the asymptote. And over here, I know it's going out to the level 1, and here it's also going to the level 1. Okay? Now, there's an issue. I can almost finish this graph now. I almost have enough information to finish it. But there's one thing which is making me hesitate a little bit. And that is, I don't know, for instance, over here, whether it's going to maybe dip below and come back up or not. So what does it do here? Can anybody see? Yeah. It can't dip below because there are no critical points. What a precise and correct answer. So that's exactly right. The point here is that because f prime is not 0, it can't double back on itself because there can't be any of these horizontal tangents. All right? It can't double back, so it can't backtrack. So sorry, if f prime is not 0, f can't backtrack. All right? And so that means that it doesn't look like this. It just goes like this. All right? So that's basically it. That's practically the end of the problem. It goes like this. All right, now you can decorate your thing, right? You may notice that maybe it crosses here the axes. You can actually evaluate these places and so forth. We're looking right now for qualitative behavior. In fact, you can see where these places hit, and it's actually a little higher up than I drew. Maybe I'll draw it accurately so that you can see it, as we'll see in a second. All right. Anyway, so that's what happens to this function. Now, let's just take a look in a little bit more detail by double checking. So we're just going to double check what happens to the sign of the derivative. And in the meantime, I'm going to explain to you what the derivative is and also talk about the second derivative. So first of all, the trick for evaluating the derivative is an algebraic one. I mean, obviously, you can do this by the quotient rule, but I just point out that this is the same thing as this, all right? And now it has whoops, that should be a 2 in the denominator. And so now this has the form 1 minus 1 over x plus 2. So this makes it easy to see what the derivative is, because the derivative of a constant is 0, right? So this is, derivative is just going to be, switch the sign. This is what I wrote before, all right? And that explains it. But incidentally, it also shows you that this is a hyperbola, right? These are just two curves of a hyperbola. Okay, so now let's check the sign. It's already totally obvious to us that this is just a double check. We didn't actually even have to pay any attention to this. It had better be true. This is just going to check our arithmetic. Namely, it's increasing here, it's increasing there. That's got to be true. And sure enough, this is positive. As you can see, it's 1 over a square. So it is increasing, so we checked it. But now there's one more thing that I want to just have you watch out about. So this means that f is increasing on the interval minus infinity x to minus 2, and also from minus 2 all the way out to infinity. So I just want to warn you, you cannot say, don't say f is increasing on minus infinity, infinity, or all x. Okay, this is just not true. All right, I've written it on the board, but it's wrong. I better get rid of it. There it is. Get rid of it. Okay, and the reason is, so first of all, it's totally obvious. It's going up here, but then it went zooming back down there. And here, this was true, but only if x is not negative 2. So there's a break, and you've got to pay attention to the break. So basically, the moral here is that if you ignore this place, it's like ignoring Mount Everest or the Grand Canyon. You're ignoring the most important feature of this function here. If you're going to be figuring out where things are going up and down, which is basically all we're doing, you'd better pay attention to these kinds of places. All right, so don't ignore them. All right, so that's the first remark. And now there's just a little bit of decoration as well, which is the role of the second derivative. So we've written down the first derivative here. The second derivative is now negative 2 over x plus 2 cubed, right? So right, I get that from differentiating this formula up here for the first derivative. And now, of course, that's also only works for x not equal to negative 2. And now we can see that this is going to be negative. Let's see, where is it negative? When this is a positive quantity, so when negative 2 is less than x is less than infinity, it's negative. And this is where this thing is concave. Let's see, did I say that right? Negative right. This is concave down. All right. And similarly, if I look at this expression, the numerator is always negative, but the denominator becomes negative as well when x is less than negative 2. So this becomes positive, right? So in this case, it was negative over positive. In this case, it was negative divided by negative. So here, this is in the range minus infinity less than x less than negative 2. And here it's concave up. All right, now again, this is just consistent with what we already guessed. And of course, we already know it in this case if we know that this is a hyperbola. That it's going to be concave down to the right of the vertical line, dotted vertical line, and concave up to the left. So what extra piece of information is it that this is giving us? Did I say this backwards? No. I don't say backwards. Okay, so what extra piece of information is this giving us? It looks like it's giving us hardly anything. And it really is giving us hardly anything. But it is giving us something that's a little aesthetic. It's ruling out the possibility of a wiggle. Okay, there isn't anything like that in the curve. Okay, it can't shift from curving this way to curving that way to curving this way. All right, that doesn't happen. So this is, these properties say there's no wiggle graph of f. Okay. All right. So, question.
Do we define increasing and decreasing based purely on the derivative, or the sort of more general definition of picking any 2 points and seeing? Because sometimes there can be an inconsistency between the two definitions.
Okay. So the question is, in this course, are we going to define positive derivative as being the same thing as increasing? And the answer is no. We'll try to use these terms separately. What's always true is that if f prime is positive, then f is increasing. But the reverse is not necessarily true. It could be very flat. The derivative can be 0, and still the function can be increasing. Okay, the derivative can be 0 at a few places. Yeah, for instance, like a cubic, some cubics. All right, other questions? All right, so that's as much as I need to say in general. I mean, in a specific case, but I want to get you a general scheme, and then I want to go through a more complicated example that gets all the features of this kind of thing. So let's talk about a general strategy for sketching. So the first part of the strategy, if you like, let's see, I have it all plotted out here, so I'm going to make sure I get it exactly the way I wanted you to say it. Oh, okay, so I have, it's plotting. The plot thickens. Here we go. All right. So plot. What is it that you should plot first? Before you even think about derivatives, you should plot discontinuities, especially the infinite ones. All right? That's the first thing you should do. And then you should plot endpoints, or ends, or x going to plus or minus infinity if there don't happen to be any finite ends to the problem. And the third thing you can do is plot any easy points. This is optional and at your discretion. You might, for instance, on this example, plot the places where the graph crosses the axis. All right? If you want to. All right, so that's the first part. And again, this is all pre-calculus. So now, in the second part, we're going to solve this equation, and we're going to plot the critical points and values. All right, in the problem which we just discussed, there weren't any. So this part was empty. All right, so the third step is to decide whether whether f prime is positive or negative on each interval. Between critical points, discontinuities. The direction of the sign, in this case, it doesn't change. It goes up here, and it also goes up here, but it could go up here and then come back down. So the direction can change at every critical point. It can change at every discontinuity, and you don't know. However, this particular step has to be consistent with 1 and 2, with steps 1 and 2. In fact, it will never, if you can succeed in doing steps 1 and 2, you'll never need step 3. All it's doing is double checking. Okay? So if you made an arithmetic mistake somewhere, you'll be able to see it. So that's maybe the most important thing, and it's actually the most frustrating thing for me when I see people working on problems, is they start with step 3, they get it wrong, and then they start trying to draw the graph, and it doesn't work because it's inconsistent. And the reason is some arithmetic error with the derivative or something like that, or some other misinterpretation. And then there's a total mess. If you start with these two steps, then you're going to know when you get to this step that you're making mistakes. People don't generally make as many mistakes with the first two steps. All right, anyway, in fact, you can skip this step if you want. But that's at risk of not double checking your work. All right, so what's the fourth step? Well, we take a look at whether f double prime is positive or negative. And so we're deciding on things like whether it's concave up or down. And we have these points, f double prime of x is equal to 0, which are called inflection points. All right? And the last step is just to combine everything. All right, so this is the scheme, the general scheme. And let's just carry it out in a particular case. Okay. So here's the function that I'm going to use as an example. I'll use f of x is x over log x. And because the logarithm, yeah, question. Yeah. So. The question is this optional? So that's a good question. Is this optional? Okay, so the question is this optional? This kind of question. And the answer is, it's more than just, so in many instances, I'm going to ask you to do this. I'm going to ask you to find these things. In many instances, I'm not going to ask you to. I strongly recommend that if I don't ask you to do it, that you not try, because it's usually awful to find the second derivative. Anytime you can get away without computing a second derivative, you're better off. So in many, many instances. On the other hand, if I ask you to do it, it's because I want you to have the work to do it. But basically, if nobody forces you to, I would say never do step 4 here. All right? Yeah. Other questions? All right. So we're going to force ourselves to do step 4, however, in this instance. But maybe this will be one of the few times. All right. So here we go, just for illustrative purposes. Okay. Now, so here's the function that I want to discuss. And the range has to be x positive because the logarithm is not defined for negative values. So the first thing that I'm going to do is I'd like to follow the scheme here, because if I don't follow the scheme, I'm going to get a little mixed up. So the first part is to find the singularities, that is, the places where f is infinite. And that's when the logarithm, the denominator, vanishes. So that's f of 1 plus, if you like. So that's 1 divided by log of 1 plus, which is 1 over 0 with a little bit of positiveness to it, which is infinity. And second, we do it the other way, and not surprisingly, this comes out to be negative infinity. All right? Now, the next thing I want to do is the ends. So I called these the ends. And there are two of them. One of them is f of 0 from the right, f of 0 plus. So that is 0 plus divided by log 0 plus, which is 0 plus divided by, well, log of 0 plus is actually minus infinity. That's what happens to the logarithm. It goes to minus infinity. So this is 0 over infinity, which is definitely 0. There's no problem about what happens to this. The other side, so this is the end. This is the first end, right? The range is this. And I just did the left endpoint. And so now I have to do the right endpoint. I have to let x go to infinity. So if I let x go to infinity, I'm just going to have to think about it a little bit by plugging in a very large number. I'll plug in 10 to the 10th here, just to see what happens. So if I plug in 10 to the 10th into x log x, I get 10 to the 10th divided by the natural log of 10 to the 10th, which is 10 to the 10th times 10 times log 10. So the denominator, this number here is about 2 point something. All right, 2.3 or so. So this is maybe 230 in the denominator, and this is a number with 10 zeros after it. So it's very, very large. I claim it's big. And that gives us the clue that what's happening is that this thing is infinite. So in other words, our conclusion is that f of infinity is infinity. Okay, so what do we have so far for our function. We're just trying to build the scaffolding of the function. And we're doing it by taking the most important points. And from a mathematician's point of view, the most important points are the ones which are sort of infinitely obvious, or the ends of the problem. So that's where we're heading here. We have a vertical asymptote, which is at x equals 1. Right here, so this is x equals 1. And we have a value, which is that it's 0 here. And we also know that when we come in from the, we come in from the left, that's f of 1 from the left, we get negative infinity, so it's diving down. It's going down like this. All right? And furthermore, on the other side, we know it's climbing up, so it's going up like this. All right, maybe I'll just start it a little higher than that. All right, so far, this is what we know. Oh, and there's one other thing that we know. When we go to plus infinity, it's going back up. All right, so far we have this. Now, already, it should be pretty obvious what's going to happen to this function. So there shouldn't be many surprises. It's going to come down like this. It's going to go like this. It's going to turn around and it's go back up. All right? That's what we expect. So we don't know that yet, but we're pretty sure. All right? So at this point, we can start looking at the critical points. We can do our step 2 here. I'm going to leave a little bit more room here. And see what's happening with this function. So I have to differentiate it. And this is the quotient rule. So remember, the function is up here, x divided by log x. So I have a log x squared in the denominator. And I get here, the derivative of x is 1. So I get 1 times log x minus x times the derivative of log x, which is 1 over x. So all told, that's log x minus 1 divided by log x squared. All right, so here's our derivative. And now, if I set this equal to 0, at least the numerator is 0 when x is equal to e. The log of e is 1. Okay, so here's our critical point. And we have a critical value, which is f of e. And that's going to be e divided by log e, which is e again, because log e is 1. So now I can also plot the critical point, which is down here. And there's only one of them, and it's at EE. Right, that's kind of not to scale here because my blackboard isn't quite tall enough. It should be over here and then at slope 1. But I dipped it down, all right? So this is not to scale, and indeed that's one of the things that we're not going to attempt to do with these pictures, is to make them to scale. So the scale's a little squashed. All right, so far I have this critical point, and in fact, I'm going to label it with a C. Whenever I have a critical point, I'll just make sure that I remember that that's what it is. And since there's only one, the rest of this picture is now correct. That's the same mechanism that we used for the hyperbola. Namely, we know there's only one place where the derivative is 0, so that means there are no more horizontals, so there's no more backtracking. It has to come down to here, get to there, and this is the only place it can turn around, goes back up. It has to start here and it has to go down to there. It can't go above 0. It's do not pass go, do not get positive. It has to head down here, all right? So that's great. That means that this picture is almost completely correct now, and the rest is more or less decoration. We're pretty much done with the way it looks, at least schematically. Okay, however, I am going to punish you. As I warned you, we are going to go over here and do this step 4 and fix up the concavity, all right? And we're also going to do a little bit of that double checking. Okay, so now let's again, I want to emphasize, we're going to do a double check. This is part 3, but in advance, I already have, based on this picture, I already know what has to be true. That f is decreasing on 0 to 1. F is also decreasing on 1 to e. And f is increasing on e to infinity. All right, so already, because we plotted a bunch of points, and we know that there aren't any places where the derivative vanishes, we already know it goes down, down, up. That's what it's got to do. Now, we'll just make sure that we didn't make any arithmetic mistakes now by actually computing the derivative, or staring at it anyway, and making sure that it's correct. Okay? So first of all, we just take a look. The numerator, so f prime, remember, was log x minus 1 divided by log x squared, the quantity squared. So the denominator is positive. So let's just take a look at the 3 ranges. So we have 0 less than x less than 1. And on that range, the logarithm is negative. So this is negative divided by positive, which is negative. That's decreasing. That's good. And in fact, that also works on the next range, 1 less than x less than e. It's negative divided by positive. And the only reason why we skipped 1, again, is that it's undefined there. There's something dramatic happening there. And then at the last range, when x is bigger than e, that means the logarithm is already bigger than 1, so the numerator is now positive, and the denominator is still positive, so it's increasing. So we've just double-checked something that we already knew. All right, so that's pretty much all there is to say about step 3. So this is checking the positivity and negativity. And now step 4. There is one small point which I want to make before we go on, which is that sometimes you can't evaluate the function or its derivative particularly well. So sometimes you can't plot the points very well. And if you can't plot the points very well, then you might have to do 3 first to figure out what's going on a little bit. All right, you might have to skip. All right, so now we're going to go on to the second derivative, but first I want to use an algebraic trick to rearrange the terms, and I want to notice one more little point, which as I say, this is decoration for the graph. So I want to rewrite the formula. Maybe I'll do it right over here. Another way of writing this is 1 over log x minus 1 over log x squared. All right, so that's another way of writing the derivative. And that allows me to notice something that I missed before. When I solved the equation log x minus 1, this is equal to 0 here, this equation here, I missed a possibility. I missed the possibility that the denominator could be infinity. All right? So actually, if the denominator is infinity, as you can see from the other expression there, it actually is true that the derivative is 0. So also when x is equal to 0 plus, the slope is going to be 0. And let me just emphasize that again. If you evaluate using this other formula over here, this is 1 over log 0 plus minus 1 over log 0 plus squared. That's 1 over minus infinity minus 1 over infinity, if you like, squared. Anyway, it's 0. All right? So this is 0. The slope is 0 there. That is a little piece of decoration on our graph. It's telling us, going back to our graph here, it's telling us that this is coming in with slope horizontal. So we're starting out this way. All right, that's just a little start there to the graph. It's horizontal slope. So there really were two places where the slope was horizontal. Now, with the help of this second formula, I can also differentiate a second time. So it's a little bit easier to do that. If I differentiate 1 over the log, that's minus log x to the minus 2 times 1 over x plus 2 log x to the minus 3, 1 over x. All right? And that, if I put it over a common denominator, is x log x cubed times, let's see here. I guess I'll take the 2 minus log x. Okay? So I've now rewritten the formula for the second derivative as a ratio. Now, to decide the sign, you see there are two places where the sign flips. The numerator crosses when the logarithm is 2, that's going to be when x is e squared. And the denominator flips when x is equal to 1. That's when this, the log flips from positive to negative. Okay? So we have a couple of ranges here. So first of all, we have the range from 0 to 1. And then we have the range from 1 to e squared. And then we have the range from e squared all the way out to infinity. So between 0 and 1, the numerator is, well, this is a negative number, and this, so minus the negative number is positive. So the numerator is positive. And the denominator is negative because the log is negative and it's taken to the third power, so this is a negative number. So it's positive divided by negative, which is less than 0. That means it's concave down. All right? So this is a concave down part. And that's a good thing because over here this was concave down. So there are no wiggles. It goes straight down like this. And then the other two pieces are f double prime is equal to, well, it's going to switch here. The denominator becomes positive. So it's positive over positive. So this is concave up. And that's going over here. But notice that it's not the bottom where it turns around. It's somewhere else. All right? So there's another transition here. This is e squared. This is e. So what happens at the end is, again, the sign flips again because the numerator, now when x is bigger than e squared, becomes negative. And this is negative divided by positive, which is negative. And this part is concave down. And so we didn't quite draw the graph right. There's an inflection point right here, which I'll label with an I. And it makes a turn the other way at that point. All right, so there was a wiggle. There's the wiggle. Still going up, still going to infinity, but kind of the slope of a mountain. All right, it's going the other way. All right, this point happens to be e squared over 2. Okay, so that's as detailed as we'll ever get. And indeed, the next game is going to be avoid being this detailed. So let me introduce the next subject, which is maxima and minima. Okay, now, maxima and minima maximum and minimum problems can be described graphically in the following way. Suppose you have a function. All right, here it is. Okay. Now, find the maximum. All right. Aha. And find the minimum. Okay? So this problem is done. Okay? The point being that it is easy to find max and the min with the sketch. Okay? It's very easy. The goal, the problem is that the sketch is a lot of work. We just spent, 20 minutes sketching something. We would not like to spend all that time every single time we want to find a maximum minimum. So the goal is to do it with, so our goal is to use shortcuts. And indeed, as I said earlier, we certainly never want to use the second derivative if we can avoid it. And we don't want to decorate the graph and do all of these elaborate, subtle things which make the graph look nicer and really are aesthetically appropriate, but are totally unnecessary to see whether the graph is up or down. All right? So let me just, so essentially, this whole business is out, which is a good thing. All right? And unfortunately, those early parts are the parts that people tend to ignore, and which are often very important. So let me just first tell you the main point here. So the key idea. Key to finding the maximum. So the key point is we only need to look at critical points well, that's actually what it seems like to in many calculus classes, but that's not true. This is not the end of the sentence. And endpoints and points of discontinuity. So you must watch out for those. If you look at the example that I just drew here, which is the one that I carried out, you can see that there are actually 5 extreme points on this picture. So let's switch, and we'll take a look. There are 5 places where the max or the min might be. There's this important point. This is, as I say, the scaffolding of the function. There's this point. There's down at minus infinity. There's this, and there's this. Only 1 out of 5 is a critical point. So there's more that you have to pay attention to on the function, and you always have to keep the schema, the picture of the function in the back of your head, even though this may be the most interesting point and the one that you're going to be looking for. So we'll do a few examples of that next time.